At the start of the 20th century, scientists discovered that the tiny atom was not a solid marble, but a complex world of charges and energy. New ideas in quantum mechanics and nuclear physics hinted that the building blocks of matter hid powerful secrets inside. In 1938, experiments in Europe showed that the nucleus of uranium could be split into pieces, releasing extra neutrons and a burst of energy. This process, called nuclear fission, suggested that a chain reaction might be possible, multiplying that energy many times over. These discoveries arrived just as Europe was sliding toward another war. Laboratories that once welcomed students from many countries now felt the pressure of dictatorships, racism, and military demands. The same science that explained stars also interested generals. Many of the world's best physicists, including Leo Szilard, Enrico Fermi, and Niels Bohr, fled Nazi persecution and war. They carried their notebooks and ideas to safer countries, but also carried growing fear about how their knowledge might be used. Szilard realized that if he could imagine a bomb powered by nuclear fission, German scientists could imagine it too. With Hitler already at war with Europe, the idea of a Nazi atomic weapon felt like a nightmare that might actually come true. To warn the United States, Szilard helped draft a letter describing the danger of a German atomic bomb and asked Albert Einstein to sign it. Einstein's famous name would help make sure political leaders took the warning seriously. In 1939, the letter reached President Franklin D. Roosevelt. After advisors explained the possibility of a new kind of bomb, he decided that the United States could not ignore it and ordered a series of committees to explore the idea quietly. At first, atomic research in the United States was scattered among universities and small advisory groups. Reports flowed in, but progress was slow. As war spread and new experiments confirmed the power of fission, calls for a larger, organized effort grew louder. In Britain, a secret study known as the Maud Report concluded that a fission bomb was not only possible, but might be built in time to affect the war. Sharing this report with the United States helped convince leaders that a crash program was necessary. By 1942, the project was growing too large and urgent for small committees. The U.S. Army Corps of Engineers took charge. To lead it, they chose Colonel Leslie Groves, an engineer who had just helped oversee the construction of the Pentagon. The new effort received an ordinary-sounding name to hide its extraordinary goal, the Manhattan Engineer District. Behind that plain title was the most ambitious secret research and construction program of the war. Groves needed a scientific director who could unite brilliant but strong-willed physicists. He chose J. Robert Oppenheimer, a theorist from California who had never run a giant lab but could see the whole project in his mind at once. Under the stands of a football stadium in Chicago, Enrico Fermi and his team stacked blocks of graphite and uranium into a careful pile. In December 1942, they achieved the first controlled, self-sustaining nuclear chain reaction, proving that reactors and bombs were truly possible. With proof of principle in hand, Groves and Oppenheimer faced a daunting task: build massive factories, secret cities, and a top-level laboratory, all while the war raged. The Manhattan Project would cost billions of dollars and employ hundreds of thousands of people. The project needed places with space, power, water, and isolation. Groves searched for remote valleys, riverbanks, and mesas where entire new communities could be built, but kept off most maps and out of the public eye. At Oak Ridge, Tennessee, engineers constructed enormous plants filled with pipes, giant magnets, and spinning machinery. Their job was to separate a rare form of uranium needed for a bomb from the more common kind found in nature. Near the Columbia River at Hanford, Washington, the project built some of the first large-scale nuclear reactors and chemical separation plants. These facilities created a new element, plutonium, which would fuel a different type of weapon. In Chicago, the Metallurgical Laboratory, often called the Met Lab, studied how reactors worked, how to handle irradiated fuel, and what health risks radiation posed. It became a brain center supporting the far-flung production sites. Workers and families moved to Oak Ridge, Hanford, and other sites, often without being told exactly what they were building. They lived in quickly assembled houses and dormitories, with schools, shops, and dances behind guarded gates. Security officers monitored mail, checked badges, and reminded everyone, "Loose lips sink ships." Even so, spies working for the Soviet Union managed to pass key information out of the project, helping other nations build their own bombs later. Building giant plants so quickly also scarred the environment. Forests were cleared, farmland taken, and rivers warmed and contaminated. At the time, wartime urgency overshadowed these questions. but the effects would linger for generations. High on a remote New Mexico mesa, the Manhattan Project built Los Alamos, the secret laboratory where the actual bombs would be designed. Oppenheimer moved there and called it his desert university, a place where theory and hardware would finally meet. Physicists, chemists, engineers, and their families formed a strange community. By day they wrestled with equations and experiments. By night they ate in shared mess halls, played music, and took walks under the bright desert stars, all behind fences and code words. Los Alamos pursued two designs: a simpler gun-type bomb using enriched uranium and a more complex implosion bomb using plutonium. Each design required new calculations, prototypes, and daring test shots out in the canyons. Plutonium from Hanford would not work safely in the simple design, so the team had to invent an implosion method that crushed a core evenly from all sides. This demanded carefully shaped explosive lenses and extremely precise timing circuits. Experiments at Los Alamos sometimes came uncomfortably close to disaster. Critical assemblies of fissile material had to be handled with great care, and a few accidents reminded everyone how powerful and risky their work really was. To release tension, the lab grew its own culture of jokes, cartoons, and nicknames. Projects received code names. The first test device became the gadget, and Oppenheimer wandered between groups, quoting poetry and asking sharp questions. Far from Los Alamos, a special bomb group, the 509th Composite Group, trained with modified bombers to deliver strange new weapons. They practiced long-range flights, precise drops, and strict secrecy, often without being told exactly what the payloads would be. By early 1945, enough material and designs were coming together, but there was little time. Groves pressed for speed to end the war, while Oppenheimer struggled to ensure that the complex devices would work on the very first try. For the first full nuclear test, the team picked a remote desert area in New Mexico that Oppenheimer nicknamed Trinity. The emptiness of the Jornada del Muerto made it easier to keep secrets and reduce danger to nearby towns. At Trinity, workers assembled the test device nicknamed the Gadget, a plutonium implosion bomb placed on top of a tall steel tower. Technicians checked cables, detonators, and instruments again and again, knowing there would be only one first test. Some early calculations had raised a frightening question. Could a nuclear explosion ignite the atmosphere and destroy the world? More careful work showed the risk was essentially zero, but the fact that scientists had to ask the question shows how new and unknown this territory was. Before dawn on July 16, 1945, scientists and officers gathered in bunkers and control posts miles from the tower. Some placed bets on how powerful the blast would be. Others simply watched nervously as the final minutes ticked away. When the countdown reached zero, the gadget exploded in a blinding flash that turned night into day. A great fireball and rising mushroom clouds signaled that humanity had entered a new and dangerous era. Some onlookers cheered, others stood silent. Groves saw proof that his project had succeeded. Oppenheimer later recalled lines from ancient scripture, feeling both pride in the achievement and dread about what the weapon could do. Reports of Trinity's success were rushed to Allied leaders meeting in Europe. They now knew the bomb worked and began thinking about how it would affect strategy, peace talks, and the final shape of the war against Japan. While the bomb was being tested, fighting in the Pacific remained brutal. Island battles had cost many lives, and planners expected an invasion of Japan to be even more costly for soldiers and civilians alike. Committees of military officers and scientists discussed possible uses for the new weapon. Some hoped for a demonstration over an empty area. Others argued that only a devastating strike on a city would shock Japan into surrender. A group called the Interim Committee advised President Harry Truman on nuclear policy. After considering options, they recommended using the bomb against selected Japanese cities without prior warning, hoping to end the war quickly. Planners chose target cities that had military or industrial importance and had not yet been heavily damaged by bombing. Hiroshima and Nagasaki were on the list. Weather, terrain, and visibility all played roles in the final choices. In the final weeks, the Allies dropped leaflets over some Japanese cities warning that terrible destruction was coming, though they did not explain exactly what kind. Broadcasts urged Japan's leaders to surrender or face prompt and utter destruction. On August 6, 1945, a single bomber dropped a uranium gun-type bomb over Hiroshima. A moment later, a powerful explosion destroyed much of the city and killed tens of thousands of people, with many more injured or sickened in the days and years to come. 3 days later, a plutonium implosion bomb was dropped on Nagasaki. The city's hills and valleys partly shaped the damage, but the human cost was again enormous and heartbreaking. Combined with months of conventional bombing and a Soviet declaration of war, the atomic attacks pushed Japan's leaders to accept surrender. World War II, the deadliest conflict in human history, finally came to an end, but the nuclear age had just begun. After the war, many Manhattan Project scientists struggled with what they had helped create. Oppenheimer spoke about having blood on his hands. Szilard and Einstein wished more had been done to warn against using the bomb on cities. Oppenheimer later opposed building some new kinds of nuclear weapons and argued for international control. During the Cold War, he was accused of being disloyal, and a security hearing stripped him of his clearance, turning the project's famous leader into a public warning. The secret of the atomic bomb did not stay with one country. The Soviet Union soon developed its own weapons, and some scientists, including Edward Teller, pushed for even more powerful hydrogen bombs, beginning a dangerous nuclear arms race. For ordinary people, the nuclear age meant air raid drills, fallout shelters, and classroom films teaching children to duck and cover. The idea of sudden massive destruction hung over daily life in many countries. Leaders and scientists also tried to steer nuclear technology toward peaceful uses. Nuclear power plants, medical treatments, and research reactors showed that the same science could light cities and help fight disease, not just destroy. Test ban movements, peace marches, and international treaties tried to limit nuclear testing and reduce stockpiles. Although thousands of weapons still exist, global pressure and diplomacy have helped prevent them from being used again so far. The Manhattan Project proved what humans can do when huge resources and brilliant minds work together under pressure. It also showed how science and war can combine to create dangers that last far beyond any one conflict or generation. Our tiny scientists remind us that ideas can be more powerful than any army. By learning about the Manhattan Project, we can better understand why choices about technology, weapons, and responsibilities still matter so much today.